Hey everyone, welcome back to the second tutorial of the xHCI driver development series, and in this part we'll focus on resetting the controller. As you remember in the previous part, we were able to read various controller information from the capability register set. Well, today we're going to touch upon and use the operational registers to communicate with the controller and tell it to stop running and then reset itself. This is important because when your computer turns on, the BIOS actually does a lot of what we're doing now and sets up the controller and configures it in a minimal way that would allow the BIOS to support USB keyboard and mouse, for example. Well, you may think that that is really nice and we could just continue using it in the state that the BIOS left it in, but actually no, we can't. Well, in theory you could, and someone on the OS Dev forums tried, but that almost never leads to anything good. Because different BIOSes leave the controller in sometimes very different states, oftentimes variable and unknown, and configured to use data structures that you potentially have no access to. Therefore, it's a pretty good idea to reset the controller ourselves when the operating system takes over and is initialized, and that way we can configure the controller in a way that we like, and most importantly, a consistent way that we're fully aware of and can control. With that in mind, let's get started. First thing I want to quickly do is add a function to dump and print the operational registers, just like we did with the capability registers. This will be really useful to see what the different configured values were left over from the BIOS setup, and after the reset a lot of them will get zeroed out, so we could compare and see the before and after. Since this is literally just a bunch of print statements, I have them copied over here on the side just to speed up the process, otherwise this video would literally take forever. Let's now go ahead and call it right after our last call to print the capability registers. There you go, and let's recompile and run the project. Great. As you can see, we have a bunch of values in place for most of the registers, which we will all go over in time, don't worry. But notice how values for CRCR and the field after look like physical addresses. That's because they are, and those addresses look like boot time addresses allocated by the BIOS. Now that we have this information, let's go over what the reset sequence would look like for the xHCI controller. As we saw in the printed output, there are two very important operational 32-bit registers, USB command and USB status. Every bit in each of them has a meaning, and it is either a read-only or a read-write bit, and you can find all that information either in the official spec or the xHCI common.h header that I provided. For now though, we're only going to worry about the following bits. The run stop bit in the command register is used to either start or stop the controller. It is a read-write bit, meaning if you write a 0 to it, it will essentially ask the controller to stop its execution. Similarly, if you write a 1 to it, it will tell the controller to start running again. The second bit in the command register is the host controller reset bit, which is exactly what we need, and if you write a 1 to it, it will initiate the controller reset sequence. Finally, the USB status bits are exactly that, they provide status information, and the ones we care about right now are the HC halted bit, which indicates whether the controller is currently in the running execution mode or not. The controller not ready bit is used to indicate whether there is a pending operation and whether the controller is not ready to receive certain register writes at the moment. And finally, the host controller error bit, which just indicates if there was a critical error during the host controller execution pipeline. So now onto the reset sequence steps. We, as the OS driver, should first tell the controller to stop running by clearing the run stop bit. As a response, the xHCI controller will assert the HC halted and not ready bits. We then write a 1 into the HC reset bit and wait up to 1 second. This will then be followed by the controller clearing the not ready and the host controller reset bits. And at this point, the controller has successfully been stopped and reset. Let's now dive back into the code and start implementing this. Let's first start by creating the reset host controller function. And let's here create the definition in the CPP file. Great. So the first thing that we need to do is clear the run stop bit. In order to do that, according to the specification, we have to first read the full 32-bit value of the command register. Then, in our local variable, we clear or set the appropriate bits. And finally, we have to write the full 32 bits back into the register as a single write. Then we have to wait for the halted bit to be set. And for that, we're going to use a timeout of 200 milliseconds and spin in a loop, continuously checking until the bit gets set. As a next step, we have to perform the same read update write back method to set the host controller reset bit. And then, in a similar fashion, we have to spin and wait for the host controller reset and the controller not ready bits to be cleared. Be careful here, and remember that the reset bit is in the USB command register, and the not ready bit is in the USB status register. After this is done, we're going to insert a small delay just to ensure that on some real hardware, the controller has enough time to finish the reset internally. As a final step, we're going to go through the operational registers and make sure that the appropriate ones are zeroed out. See, this wasn't so bad. We can now finally call the reset controller function in our driver init code. We're also going to log the operational registers again to see the values before and after. And there you go. As you can see, our controller's operational registers have now been zeroed out, and the USB status register indicates that the controller is no longer running because the HC halted bit, which is bit 0, is set. And this is it for today. We have successfully reset the xHCI controller. I have only briefly explained the purpose of the registers and their bits involved, but I highly encourage you to go look at the official xHCI spec. Literally just Ctrl F search for these registers and read through the descriptions of these bits. I guarantee you that if you bump into any problems, reading this spec will help you more than anything else. It should be your starting point. In the next part, we're going to go over the necessary steps to properly configure and set up these operational registers, which will directly lead us into starting the xHCI controller ourselves and subsequently be able to send transfer requests and commands to it, which is probably going to be my favorite part. So stay tuned and see you in the next video.